All right, welcome back, everybody. So we have Hal Schenck from Auburn joining us virtually. Hi, Hal.
Hi, guys and
And he will
gals.
tell and gals, and he will tell us about free curves, eigenschemes, and pencils of curves. Take it away, Hal.
So thanks very much for the invitation. I'm really, really sad that I'm not there with such in such a nice venue with such a nice group of people. And especially I'm sad not to be there to harass Frank. So I am harassing him a little bit. So instead of having a shirt from Churchill College, which was where Frank was at Cambridge, I'm wearing Fitzwilliam. So that's my minor act of harassment. So this is joint work with Roberto Di Gennaro and Giovanna Alardi, who are both at Napoli. Rosamiro Roig, who's in Barcelona, and Jean Valles, who is at Po. So it's an Italian, Spanish, French, and US team. So before I start going, let me say just a little bit of background on what the problem is. So the big picture to keep in mind here is the following. We're going to have some variety, and that variety will be smooth. And in fact, we're going to be interested in projective or affine space. So there's a tangent bundle on that variety. And then if I take a hypersurface, I can take the subbundle of the tangent bundle where if I take a tangent vector, it's tangent to that hypersurface. So this is going to be a subbundle of the tangent bundle. So these are usually called, this is called the logarithmic tangent bundle. And so there's a dual bundle, which is called the sheaf, well, or vector bundle if your hypersurface is smooth, but it's the bundle of logarithmic or the logarithmic cotangent bundle. And here you're going to have one forms which are allowed to have a simple pole along that hypersurface. So these are geometric objects that appear in Grothendieck's algebraic Durham theorem. And so the question that we're going to be asking is about the behavior of this logarithmic tangent bundle or its dual is when does it split as a sum of line bundles? And so this sounds like a very abstract algebro-geometric question, but the jumping off point is when our hypersurface is an arrangement of hyperplanes. So this turns into a problem in combinatorial discrete geometry. And the takeaway from the talk is that there's a big question in the field, which we'll come to shortly, which is still open. So this talk will not solve a big open conjecture, but everybody here will learn about a very nice conjecture in enumerative geometry, which is open. So, and it's also something that is very amenable to computation and experiment. So it's a fun thing to play with. So if you zone out during my talk, impossible, that would never happen, but you can start coding right away. It takes 3 lines, 10 lines of code, and you can start experimenting. So that's the background and the big picture. And so let's get moving. So here's some definitions. We're going to be working in an algebraically closed field of characteristic 0. You can do this in a finite field, and there's lots of interesting number theoretic problems that are connected to this, but we're going to stay in characteristic 0. We're going to be working in projective space and projective n space. So underlying projective space, that's proj of the usual polynomial ring in n+1 variables. And here's the central player in our investigation. Well, the start is that this is the algebraic version of the tangent bundle is just the module of derivations. So this is R is our polynomial ring. And this module der K of R, K is our field, this is just a free module whose basis is given by d dxi. And so these are, we think of these as polynomial differential operators, right? These are, the d dxi is a differential operator, and then it has polynomial coefficients. So of course, this der K of R can be fed a polynomial, and it will spit out a polynomial. So this is a free module of rank n+1. And so then, so what are we looking at here? Let me get this stuff out of the way so I can see the bottom of my slide. Collapse that, okay. And then this is what I defined was this, I have a hypersurface defined by, in this case, because we're thinking projectively, F is going to be some homogeneous form. And then I want these logarithmic vector fields. So these are going to be, and algebraically, I have this polynomial differential operator, which when I feed it the defining polynomial of my
Hey,
hypersurface.
Hal.
Yes.
What's X?
X is the ambient space. So I said, this is right now, this is X. For us, X is going to be projective space, but this applies more generally. So great question. In general, this is a general definition for this logarithmic tangent bundle. but for us, X will be projective space.
Thanks.
Okay, and so then this algebraic operation is very easy. The elements of this, and you can bounce back and forth between sheaves on projective space or graded modules over the polynomial ring. So these are just going to be these polynomial differential operators, which when we feed it are defining polynomial for the hypersurface. It just spits out a multiple of f. So this is a very simple algebraic condition. The other thing I want to point out is f is going to be reduced. So this, we don't have f can factor. And in fact, like I said, this jumping off point will be where f is a product of linear forms, but there won't be any repeats in that. So this is a reduced, but it doesn't have to be irreducible divisor. So this is the setup, or I guess, dramatis persona. And so, and here's the definition. We say that a divisor is free if this is a free R module. And we'll see examples of this in just a second. So the first thing to point out is that there's it's obvious that this DARE of F is non-empty, and it's because we have the Euler relation. So if we have a homogeneous polynomial F, and I apply the Euler derivation, which is this delta sub E to F, we know that we just get out F again with multiplied by its degree. So that's Euler's relation. So, and in fact, it turns out that Euler operator is going to generate a free summand of the module DARE of F. And so any derivation can be written as some delta prime plus a multiple of the Euler derivation. And the idea is basically this delta prime will be a polynomial differential operator which eats F and spits out 0. So again, that's only because the Euler operator returns a multiple of F. And so if we rip that Euler operator off of some arbitrary derivation, we get a derivation which vanishes on F. And this is going to be important because it gives us an easier way to think about this module DARE of F. And the point is, so this is what we just said, that this Euler operator generates a free summand of the module, and then the DARE 0 of F are these derivations which eat F and spit out 0. And this is a familiar object to those of us who work in commutative algebra or computational commutative algebra or computational commutative algebra and combinatorics. It's simply the syzygies on the Jacobian ideal. And the reason that this is the case is if you think about it, what's a syzygy on the Jacobian ideal? Well, the Jacobian ideal is exactly partial f partial x naught up through partial f partial xn. And then a syzygy is some polynomial g0 up through gn, which dots to 0 with the Jacobian ideal. And that's exactly, if we just sort of think of those gi's as being the coefficients of our derivation, that's exactly something which eats f and spits out 0. So the syzygies of the Jacobian ideal correspond to this module DARE 0 of f. And so then we say that this hypersurface is a free hypersurface exactly when this module of derivations is a free module. It splits as a direct sum of copies of R. We'll see, as I mentioned, if it's terrible to have abstract definitions without examples. So we'll see an example in a second. And it's an easy observation that the sum of these shifts, these are simply the R of minus A1 through minus AN, those are simply going to be the degrees of the polynomials that appear in this syzygy. And since it's a syzygy on the Jacobian ideal, F was degree D, then the sum of these AIs has to add up to the degree of the Jacobian ideal minus 1. So what? So this is what we just said. This is delta. We've got this Jacobian ideal, and our DARE 0 of F is simply the kernel of that. So think of this again. This is linear algebra with polynomials. So I have an n plus 1 by 1 matrix given by the partials of our hypersurface, and the kernel of that n plus 1 by 1 matrix is our module derivations. So this is the first. This is the reason that this talk should. You should stay awake in this talk, is that there's a beautiful paper from 45 years ago in Invenciones by Orlik and Solomon, where they computed the cohomology ring of the complement of a hyperplane arrangement. So I have some hyperplane arrangement in projective space, and then I take its complement that has a cohomology ring, And it has a beautiful presentation. So for those of you who like Stanley-Reisner rings, which are rings associated to simplicial complexes, the Orlik-Solomon algebra is very similar in flavor to the Stanley-Reisner ring. It is a quotient of an exterior algebra with the number of generators equal to the number of hyperplanes. And the ideal that you quotient by to get this cohomology ring is determined only by the intersection lattice of the arrangement. So what's the intersection lattice? I'm using lattice not in the sense of a free Z module, but as a graded poset. And that intersection lattice has as its rank 1 elements, the hyperplanes themselves, as its rank 2 elements, the codimension 2 intersections of the hyperplanes, and so on. So this is a very combinatorial object. And this Orlik-Solomon algebra, or the cohomology ring, is given in terms of the lattice. And then the next year, Hiro Terao, in another Invenciones paper, showed that if the arrangement is free, the Betti numbers are determined by the exponents. What are the exponents? Remember, the exponents are exactly, if it's a free module, it's these AIs where it splits. And so there's these two Invenciones papers about cohomology ring of an arrangement complement and this module of derivations. And here is the conjecture. So this is an open conjecture, and that is that the freeness of the arrangement depends only on the intersection lattice. And that means that the idea that, or the picture you should keep in mind is if you have some hyperplane arrangement and you wiggle it without changing the intersection, so you don't change some place where, say, 3 hyperplanes meet in a codimension 2 space to breaking that codimension 2 intersection, then if it's free or not depends only on that combinatorics. So this is a conjecture that's been open, as you can see, for well over 40 years. And what we're going to do is investigate this conjecture in the most concrete setting. So what would be the easiest sort of arrangement? Well, that would be a configuration either of lines in P2, or you might try to generalize and say, well, maybe we'll get some insight on what happens to a line arrangement in P2, or if you like affine things, a arrangement of planes in C3 that all pass through the origin. Maybe we can obtain some insight into freeness by looking at freeness just for curves in P2. So that's where we're going to go, is talk about freeness for curves in P2. Any questions so far? Let me pause and see if anybody. I don't see any hands. Maybe Tyler or somebody can yell at me if there's a question from the audience. So that's the problem, is to understand.
Looks okay.
Say again?
No questions. You're good.
No questions. Okay. So big open question, which we won't solve. So again, you should stay interested because this is a fun problem to play with. So here's some easy combinatorics, and we're going to focus on curves in the plane. So right now we're specializing to just curves in P2, sort of almost the most concrete objects that you could imagine. Of course, if you pick up Brieskorn's book on singularities, which is about basically curves in the plane, that's, I don't know, 800-page book, and nobody likes 800-page books, right? If our curve arrangement is free, so we have a curve F in the plane of degree D. These two, and the arrangement is free. There'll be 2 generators. Remember, these are syzygies. These are relations on our Jacobian ideal. The sum of those syzygies, which are homogeneous, these are vectors of homogeneous polynomials, will be D minus 1. And then the product of that is going to be D minus 1 choose 2 minus the sum of the multiplicities of the singularities. And I should say that for a line arrangement, the multiplicity of the singularity is simply the number of points passing, number of lines passing through the points minus 1. That's not the case for general arrangements. And this is we're going to talk about the behavior of singularities in a second, but for line arrangements, and it turns out that the singularities are always something called quasi-homogeneous, and we'll see there's a very nice description of what that condition is. So here's some examples. So 2 lines are free, and the syzygy module splits this way. 3 lines through a point are free. The syzygies, one of them is degree 0, one is degree 2. A line tangent to a conic, or 3 lines that all meet sort of generically, those are both free. What are non-free things? So this might make you think that lots of arrangements are free. So first off, a smooth irreducible curve is always going to be non-free. And even if you allow nodes or cusps, this also will not be free. More sort of concretely, if I take an arrangement of lines, which is generic, so this is where we take our, pickup sticks and drop them all, and all the intersections are normal crossing. So if it's generic, that means that lines should intersect in only 2 points. As soon as, even though in this case with 3 lines, that arrangement was 3, as soon as you have 4 or more lines and it's a generic arrangement, it will not be a free arrangement. So the upshot is that if you're sort of doing computational experiments, you should think of free arrangements as being very non-generic. So those are some examples. Here's 2 interesting examples, I think. So the first one, these are this arrangement of 6 lines in P2. You can think of as the reflecting hyperplane. If you thought sort of affinely in C3, these are the reflecting hyperplanes for the A3 reflection arrangement. So I have 6 planes in C3, which we're going to draw as 6 lines in P2. And you can see that this arrangement, this is not rigid in the sense that if I wiggle the positions of these vertices but keep the combinatorics fixed, I'll still have 4 triple intersections, so that the intersections that are marked with dots are triple intersections, and then I have these 3 normal crossing points marked with stars. So this is a free arrangement. There's a reason this is a free arrangement, and that is, I'll mention this in a bit when I talk about history. The intersection lattice of this is a supersolvable lattice. So supersolvable basically means either combinatorially that you have a maximum chain of modular elements, but it has a beautiful combinatorial picture, or no, sorry, topological picture, which is if we think of the arrangement complement, what supersolvable means is that there's actually a chain of fibrations where each fiber is simply a complex line punctured in a certain number of points. The number of punctures actually corresponds to these exponents. So there's a fibration here where we have one fiber that is a C punctured in 3 points and another fiber that is a C punctured in 2 points. So now if we perturb this arrangement though and change the combinatorics. So here what I'm going to do is I'm going to take one of these lines, for example, this line right here, and move it off holding all the other lines fixed, and that breaks that middle symmetry. So now instead of having 4 triple points, I have 3 triple points. And it's an easy exercise. You don't have to do anything except use that little observation that we had a few pages ago right here, which was that if your arrangement is free, we have 2 numerical conditions. And in this case, those numerical conditions aren't satisfied. So this perturbation is not a free arrangement. And so, of course, we've changed the combinatorics, right? We've changed the combinatorics. So here is one of the earliest theorems. This is due to Sato. So, and this is more general. I'm stating it here for a curve, but it applies more generally to any hypersurface. And it says that basically for a curve, the arrangement is free exactly if I take if there's 2 derivations, remember we think of these derivations as syzygies, such that if we stack those 2 syzygies in a matrix and then add on the variables, we get a multiple of our defining polynomial f. So this is called Sato's criterion. The proof of this, which I think was not sort of the early folks who were working in hyperplane arrangements were oftentimes coming from topology. This is really an instance of something called the Hilbert-Virch theorem, which tells you about codimension 2 Cohen-Macaulay ideals and Euler's relation. And so from an algebraic standpoint, this is an easy sort of criterion for freeness. And it really is just translating this freeness condition into saying that the modulo of derivations is a free module. That means you only have, if this was an arrangement in Pn, we have exactly n in linearly independent syzygies, which have no relations on them. So this is Sato's theorem. And we're going to switch gears in a bit. And essentially the whole point of this talk is that there's an object which has appeared recently in analysis of tensors called Eigenschemes, and Eigenschemes will have a role to play, and we're essentially going to translate Sato's criterion into something related to Eigenschemes. But this is a nice, easy to use criteria to check on freeness. So what? So here's our history. So the first results on hyperplane arrangements were Sato, who proved this Grothendieck algebraic theorem, which relates if you have a divisor in a variety and want to know the cohomology of the complement of that, this is a result of Grothendieck, which is basically if the divisor has normal crossings, there's a very nice recipe for it. And Deline proved some results on reflection arrangements, so arrangements that come from the reflecting hyperplanes of some of the reflection groups. Then I mentioned this result of Orlik-Solomon, who proved a result on the cohomology ring. Sato, there's an LCS formula. This relates the fundamental group of the arrangement complement to the cohomology ring. And then there's a wonderful slew of results in the 80s that are combinatorially or about the combinatorics due to some of these names here, as well as this formula that I mentioned of Terao and Terao's freeness formulas about supersolvability and LCS formulas. There's a bunch of these papers I should mention that are in Venciennes. So this was a very, very active area in the 80s. And then more recently, there's work of Dan Cohen and Fred Cohen, Abe, DiConcino, Porchese, Dimka, Denham, Weichner. June, of course, famously proved Rota's conjecture using graphic arrangements. So if you take a graph, you can create an arrangement where your hyperplanes are simply basically xi minus xj if ei if vi vj is an edge of the graph. So you have graphic arrangements, and June proved this conjecture on unimodality via graphic arrangements, and then a whole slew of other names here. And so these are all, everything I'm talking about up to this bottom thing was all focused on hyperplane arrangements. And you could say very reasonably, well, there's still lots of open questions on hyperplane arrangements. Why would you look at hypersurfaces instead? And of course, the point is that perhaps by looking at a more general class of objects, you can obtain insight into these hyperplane arrangements. So let me pause again for a second and ask everybody okay, or any questions? So this has all just been the background and history part of the talk, and now we're going to start to move into some new things. All good?
I think you're good to go.
Everybody has coffee, right? So, okay.
Yes.
Okay, so now let's talk about hypersurface arrangements, but we're going to stay in the setting of the simplest hypersurface arrangements, which are curves in P2. So it turns out with one of my students, Stefan Toaneu, who's now at Idaho, we looked at what's the simplest generalization? Well, how about arrangements of smooth rational curves? Well, a rational curve in P2 is either a line or a conic. And so we could say, let's look at line and conic arrangements. And so what was surprising to us is that even in this rather simple extension of hyperplane arrangements or line arrangements, freeness is not combinatorial. So you can have combinatorial equivalent arrangements of lines and conics. That is, the intersections all look the same. And even if the singularities are all normal crossing, so that if you zoom, or not normal crossing, sorry, ordinary singularities. So if you have, say, D branches passing through some singular point, when you zoom in, you see D distinct tangent lines. So I'm not allowing things like two conics touching at which meet at a single point. So, but things where all the singularities are ordinary. So even there, freeness is not combinatorial. And then with Hiro Terao and Masahiko Yoshinaga, we came up with a deletion restriction theorem for curves. So the thing you might think about in the setting of a line arrangement or even a hyperplane arrangement is there's a very natural sort of inductive operation, which is if I have an arrangement of K hyperplanes, I could either remove one hyperplane and have another hyperplane arrangement with one fewer hyperplanes, but I could also restrict the hyperplane arrangement to that distinguished hyperplane. And that gives you essentially it's not always true, but it gives you sometimes a sequence which is either left or right exact, and which is sometimes exact. And so this gives you a way to relate two simpler objects, the deletion, throw away a hyperplane, or the restriction, restrict to a hyperplane to an arrangement. And so we were able to prove a deletion restriction arrangement for curves with a caveat that I'll mention later. And then Jean had some beautiful results on pencils of curves. So a pencil, if you're not it's an algebra geometric concept, but all a pencil is, when somebody says a pencil, it is a family of objects that is parameterized by a P1. And so the reason it's called a pencil is you have this line. A projective line has two parameters, A and B. So when someone talks about a pencil of curves, they mean basically you take a variable a times some defining polynomial for a curve plus another variable b times the defining polynomial for another curve, and then you let a and b vary, and that gives you a pencil of curves. And so a lot of the results on curve arrangements and understanding freeness for curve arrangements require that your singularities are something called quasi-homogeneous. So I want to talk about this quasi-homogeneity conjecture, not conjecture, condition, because the main result that I'm going to talk about today is a construction for free arrangements where we can dispense with this quasi-homogeneity. So, ideally, what you walk away from this talk is, number one, with the knowledge that there's some very interesting conjecture and hyperplane arrangements, which is combinatorial, but also that there's a useful construction of something called eigenschemes. So eigenschemes are the tool that I hope we walk away with. So here's the definition of quasi-homogeneity, and we're only going to do this for curve singularities. So we look at a point, suppose our curve is singular at that point. That is going to be quasi-homogeneous if there's basically a holomorphic change of coordinates so that the corresponding polynomial at that point is homogeneous. Now, that might not speak to you. It doesn't really speak to me. So let's talk about some other ways to view this quasi-homogeneity condition, because it's actually, there's a much nicer way to define quasi-homogeneity than this. So, and again, we're staying in the case of a singular point of a plane curve. So at a singular point, we can localize and look at the ring of power series. And there's two numbers that are associated with that singularity, which are called the Milnor and Cherena numbers. So the Milnor number is simply this formal power series ring modded out by the two partials of our defining polynomial. And the Cherena number is the dimension. These are both going to be finite dimensional vector spaces, I should say, because it's a singularity. And the Cherena number is where we take the two partials of our defining polynomial and throw in the defining polynomial itself. So obviously, the Cherena number is going to be less than the Milnor number because I've thrown in an extra equation. And for curves, Riefin proved in 1967 that you're a quasi-homogeneous singularity exactly when the Milnor and Cherena numbers are equal. And Sato generalized this to higher dimensional hypersurfaces. So these Milnor and Cherena numbers give us a way to understand quasi-homogeneity. So let's see something. So here's an example. This surprised me. I think this is indicating the subtlety of the quasi-homogeneous condition. So if we take this configuration, this is a line conic configuration. We can see that there's 5 singular points, 4 ordinary singularities, which are normal crossing. And then I also have an ordinary singularity at the origin where I have all 5 branches of the curve meeting. But you can see this is an ordinary singularity, right? I have 5 distinct tangent directions there. And so it's easy to check that this is not quasi-homogeneous. And the reason is that the degree of the Jacobian ideal is the sum of the Cherena numbers. Now, the nice thing is you can compute the degree of the Jacobian ideal purely algebraically without doing anything. You can type it in the computer and we'll spit it back out. And in this case, we get that the degree of the Jacobian ideal is 19. So the Milnor number of an ordinary singularity is just the n. If I have n branches, it's just n minus 1 squared. So the sum of the Milnor numbers here would be 1, 2, 3, 4 plus 4 squared, because 5 minus 1 squared is 16. So the sum of the Milnor numbers is 20. But you can compute using any computer algebra system that the degree of the Jacobian ideal is 19, which means in particular that even though the Milnor number at that singularity is 16, the Cherena number is 15. So this point right here is not a quasi-homogeneous singularity. Again, what's the takeaway? You cannot understand this quasi-homogeneous condition just by looking at the singularity. It's a very subtle point. Okay. So what? So here's some more examples of free line arrangements. And there's a reason I've got these free line arrangements up here. So of course, I should really have a picture. This one we've already seen, we've seen this line arrangement before. This is a very interesting arrangement, this Hessian arrangement. it consists of, it doesn't appear to be the case, but each of these cubic factors. So this is a configuration of 12 lines, and then there's this Fermat arrangement. So why do I have these things here? Well, it turns out, so this is another ingredient that we're going to discuss. I'm doing a Zoom talk. Sorry, just got someone knocking. So these are actually the union of singular members of certain pencils. And I want to say one thing about this Hessian arrangement. So if you take any smooth cubic curve, it's going to have 9 inflection points. And those 9 inflection points, there's triples of them that are actually collinear. There's 12 of them that are there. You have 12 sets of triple inflection points and those 12 lines are exactly the 12 lines that make up this Hessian arrangement. So this is a sort of related to very, very classical geometry. But what's the takeaway? The takeaway is that these free arrangements somehow are corresponding to singular fibers of certain pencils. So that's another ingredient that's going to appear later in the talk. All right, so, and here's the first theorem. So this is a theorem, a beautiful theorem, in my opinion, of Valles. So if we take a pair of reduced polynomials and look at their intersection, so this is a complete intersection. I have d squared distinct points. I take 2 homogeneous polynomials and 3 variables such that they're a complete intersection. I have not just a complete intersection, but a reduced complete intersection. So I have d squared distinct points. And then I take, I'm sorry, I'll be right back. I just have to do something. Yes, I am. I'm doing a Zoom talk. So, this theorem of Jean's from about 8 years ago says that if we take the singular curves in this pencil, right? So I have the pencil here is going to be, I take a parameter a times f and another parameter b times g, and I let a and b vary. Oh, I'm using s and t as my parameters here. Then, and I take k elements of this pencil. So I'm just taking k arbitrary curves. So I'm taking some k points s and t, and I take that union of those curves. Then that corresponding curve is free with these exponents, 2d minus 2 and d times k minus 2 plus 1, exactly when f times d, remember d was this set of all the singular curves, and f is one of these defining polynomials, it could as well be g, that the union of those singular points is contained in this dk, which is the union of the curves making the pencil. But notice we still have this hypothesis about the singularities being quasi-homogeneous. And that quasi-homogeneous, for the addition-deletion theorem that I proved with Terao and Yoshinaga, we also required the singularities to be quasi-homogeneous. And basically, the idea is that when the singularities are quasi-homogeneous, that meant the Milnor and Sharina numbers are equal, and that means you can actually understand the multiplicity of a singularity just by looking at what's going on at it. So now we're ready for our new player. So we want to dispense with this quasi-homogeneous condition, and this is the definition of an eigenscheme. And again, I'm only going to do this for polynomials that are polynomials in 3 variables. Yes.
In your last slide, go back.
Yeah.
I see a condition with f on the last line, but the pencil is defined by f and g. So what happened to g in that?
That's what I was saying, Frank. So I said it could as well be, you could use g instead. So this is equally applicable with g. So you could say fd is contained in this, or gd is contained in this. So here's the definition of the eigenscheme. So I have 3 homogeneous polynomials of the same degree. And then I do this weird construction where I take a matrix, I make them one column of a matrix. I take my variables x, y, and z. Again, we're in polynomial in 3 variables. And I take this 2 by 2, the 2 by 2 minors of this matrix, and that's going to define what we call the eigenscheme. So what are some properties of the eigenscheme? The first one is that if I have a curve that's contained in this, so P1, P2, P3 could, there's multiple things that could happen there. If P1, P2, and P3 share a common factor, right? They could share a common factor. And I have some curve that or even if they don't share a common factor, they could just define a bunch of points. if I have a curve that's sitting inside the corresponding variety, well, if the curve sits inside this variety, that would mean exactly that P1, P2, and P3 are sharing a common factor. Then C is in the eigenscheme. So if your eigenscheme contains a curve, that's actually going to mean that these polynomials were all shared a common factor. So what if they don't share a common factor? So suppose that you've got a finite set of points or even an empty set of points. You could still have your eigenscheme being codimension 1. So this is a little counterintuitive because you're thinking, okay, here's a set of polynomials that defines a 0 scheme. And then I take the 2x2s of this matrix, and you might think, well, x, y, z define the irrelevant ideal. This is probably also going to be a 0-dimensional scheme, but that's not the case. And here's an example of what could fail. And I want to talk through this just so we develop a little bit of dexterity with eigenschemes, is if my P1, P2, and P3 are as we've written down here, well, you can see that let's look at one of these 2x2 minors, x times P1 x times P2 minus y times P1. Well, I have x times P2, that's going to give me an xyf factor. And then I'm subtracting y times P1, that's going to give me a yxf factor. So those two pieces will cancel, and I get I get something times a GQ. I get y times GQ1 and an x times GQ2. So clearly that 2x2 minor given by the top 2x2, will have a factor of g, but that's a symmetric condition. So the eigenscheme will have v of g in it. So the behavior of this eigenscheme seems perhaps a little mysterious. So let's look at eigenschemes a little more. So the first thing is this is an easy exercise, that if the eigenscheme is actually finite, so when we say finite, we mean 0-dimensional, then the ideal sheaf of the eigenscheme is defined by exactly that, the syzygies of the eigenscheme are exactly given by this matrix. So, and the length is the second Chern class. Let's ignore that second Chern class. This is just, it's given as a number where, remember, n was the degree of the defining polynomial. So these all P1, P2, P3 were degree n. And so when we do have a 0 scheme, the degree of that 0 scheme is given this way. So what? So this is where I said eigenschemes are going to be related to that Sato criterion. So suppose that we do have a 0-dimensional scheme, and I'm going to take some polynomial of degree n plus 1, such that, and this is, I shouldn't have written it this way. This is just, all that this is saying is that f is a polynomial which goes through that scheme and is of degree n. So we think of this as, I guess one could think of this as saying that f is a degree n polynomial which lies in the ideal of that scheme exactly when we have 3 polynomials, q1, q2, q3 of an appropriate degree, such that the determinant of this matrix is CF. And if you remember, this is exactly Sato's criterion. So we're sort of translating Sato's criterion into some condition related to eigenschemes. So that's the first step, and this is somehow the raison d'etre, so to speak, for the eigenscheme. The eigenscheme, remember, is just these sort of the first 2 columns of this matrix. And that is, if you were just doing pattern matching and you knew Sato's criterion, you'd say, oh, maybe eigenschemes are related to this Sato's criterion because of this sort of lemma. All right, so here's the first theorem, and it's giving us a theorem about freeness. So the result of this is freeness, but it's related to this eigenscheme condition. And really what this is just taking Sato's condition and then marrying it up with the definition of an eigenscheme. So what's the theorem? Suppose that we have a derivation. And when we say the degree is A, that means the degree of these polynomials is A. And this derivation has an eigenscheme because I have these 3 polynomials, P1, P2, P3, and we're going to suppose that the eigenscheme is finite. Then if we take some polynomials, which is eaten by this derivation, right? So if I have some polynomial that the derivation eats and spits out 0, when is it free? It's free exactly when it is an element of the eigenscheme ideal. And again, this is not, this is really using Sato's criterion and translating it into eigenschemes. The one thing that is important, and I'm going to kind of gloss over this, is that these exponents being fixed is important. If you have a free curve of degree 5 with two exponents, remember that exponents sum to the degree of the curve minus 1. But if you take generators for der2, the two generators for the modular derivations, because of this condition, these are both degree 2. You could take one of those derivations, you can take linear forms and multiply it. This is a derivation because these mu and nu are generators. So if I take some multiple of each of them, it's still a derivation. But and v of f was free already, but it certainly doesn't have these exponents 3, 1, because, well, we've already said it had exponents 2, 2. So one does have to be a little bit careful with the bookkeeping, but that's sort of an aside. All right, so here's another interesting player. Oops, sorry, my bad. So here's another interesting player, and it's kind of a almost trivial observation. And so suppose that we take, and this is headed towards our construction of free curves, a construction of free curves that is new. And so if we take a pair of polynomials with no common factors, so this is going to define a complete intersection, right? So f and g are two polynomials which define a complete intersection. Then there is actually a canonical derivation associated to the pencil that these things generate. And so the canonical derivation is this matrix that we've written down here. And so if I take, and you might say, well, this is kind of BS because the dxf and the dxg, these are polynomials, and then I have these differential operators. But obviously, if I take the determinant of this matrix, what I'm going to get is a polynomial differential operator, right? So I'll have the coefficients of these partials, and then I'll have dx, dy, and dz. And so what is this? Why is this a derivation on the eigenscheme? Well, it's basically because when I plug in any multiple, if I plug in an AF plus BG and put that in with my dx, dy, dz, those are obviously linear combinations of these dxf's and dxg's, right? So if you sort of plug into these dx's, you're an element of the pencil, this determinant's going to vanish simply because when you plug it in to this matrix, you're getting 3 columns that are linearly, by construction, linearly dependent. So we have this sort of canonical derivation that's associated to a pencil, and then we have an eigenscheme that's going to be related to this canonical derivation, because this derivation has coefficients that are now that what are the coefficients? The pi's are going to be the 2 by 2 minors of this matrix over here. So if I take this submatrix, take the 2 by 2 minors, those give me an eigenscheme. And then what turns out to be the case is that eigenscheme can be written as the base locus, right? So f and g were a complete intersection. So this B is going to be a 0-dimensional subscheme. And that, again, is because f and g had no common factor. Union with this v of f, this is the P1, P2, and P3 that define our eigenscheme. It doesn't have to be finite, but when the case that's most of interesting to us is when n and m are equal, and then we define a curve exactly when the pencil contains a non-reduced curve. This is all preparation for the following proposition. So here's the first construction. This is not our main construction. So if I take a pair of reduced polynomials such that this corresponding variety, which is our eigenscheme, is finite, and we take integers such that the LCM is written this way, an and bm, and we have, because of this v of our eigenscheme is finite, we look at the associated eigenscheme. This was a finite scheme. Remember, this is just the 2 by 2 minors. This is P1, P2, P3. And then we look at the eigenscheme of that, which is, remember, a different object, because that's the minors of this matrix. The eigenscheme was the minors of this matrix of the x's and the p's. then we have a finite number of curves that are singular outside the base locus. Remember, the base locus is just where f and g both, the common zeros of f and g, so v of fg. So we have a finite number of singular curves, and then our scheme gamma, and gamma is the eigenscheme. So this is describing the eigenscheme. So this is really nice. This is a very concrete description of what this eigenscheme is. It's simply the union of the base locus. So the v of fg and this z, and z was exactly the z was this the 2x2 minors of the p1, p2, and p3. So what? So I want to talk now, we're going to have the main theorem in a second, but I want to have an example. So here's an example. Suppose I have a pencil of conics. So here's two conics. I'm going to take some scalar multiple of xc, some other scalar multiple of z squared minus xy. Then we can compute the canonical derivation. All these things are very eminently computable. We compute the canonical derivation. We find its eigenscheme has length 7, which is 1 plus 2 plus 4, which we knew. And here's the ideal of the eigenscheme. And our previous proposition shows that this is a free curve. So this is something new. We haven't seen, this is in the sort of the free divisor literature. This is a new beast. And I want to take a little pause for a minute here. So what do we have? I want to convince you that these things are also, one of the things in the title of the conference is computational. Let's do this computation. So we've got xz. I'm paying homage to the fact that the conference is in Canada, and we have z squared minus xy. So let me get out of here for a second. Let's go pull up a terminal window and do this in Macaulay 2 and for 2 seconds here. Let's see, got to make that bigger. Oops. Okay, let's do this. So here, let's do this computation in M2, Macaulay 2. Let's do, our ring is, we'll just work in a finite characteristic. We could, if you wanted to be pedantic, we could work over Q. What were our polynomials? Our polynomials were f was xz, and g was equal to z squared minus xy. Let's take the corresponding arrangement, f times g. So there's our arrangement. That's the defining equation for our curve. Let's take the Jacobian ideal of that. And now let's compute the kernel of this. So I want to do min gens of the kernel of the transpose of this matrix, right? So these are our syzygies, right? These are our three partial derivatives. I flip it, so I have a 3x1 matrix, and I want to compute the minimal generators. What are the minimal generators? Oh, one minimal generator of degree 1 and one minimal generator of degree 2. And there's two generators. This exactly says this is a free arrangement whose exponents are 1 and 2. So let's go back to this one and get back to our slideshow. All right, so this is what we just did this computation. So that's an example. And now following on with this, if we instead take three smooth curves of the pencil, our theorem says that this thing's going to be free with exponents 2 and 3. And so what's an example of three elements of the pencil? I would have something like f and g were our two defining quadrics. I take those three things and multiply them out. And notice this is bad notation. Over here, I'm going to write, this is the eigenscheme. So the eigenscheme of that thing is going to be, remember, what are we doing? For the eigenscheme, we're taking the x, y, z and the p1, p2, p3, and we're writing these as u, v, and w. So if you do the same construction instead of with two osculating conics, the theorem says that those are not free. But if we take three osculating conics, which I've drawn below here, then this is an example. What's nice about this three osculating conics, this has sort of the same behavior as our bad non-quasi-homogeneous singularity. And in fact, this singularity right here at the point, well, P is supposed to be, P is this, I see it's in my figure. The point where I'm hovering, where there's the three conics are all tangent. is a non-quasi-homogeneous singularity, but in fact, this is also a free curve arrangement. And so that is sort of illustrated by, this is the punchline, this is our main theorem, which is that if we take a pair of reduced polynomials with no common factors, and we take the 2 by 2 minors of that matrix, of the Jacobians of those, sorry, we take the Jacobian ideal of those two polynomials, that gives us a 2 by 3 matrix, then take the minors of that, that's a finite scheme, then we have this construction that says, if we take a union of a bunch of the curves in the corresponding pencil, with a certain condition on the LCMs, and we take a polynomial of a certain degree which divides this product, then that's a free curve, and it's a free curve it's a free curve with certain exponents exactly when f is in the eigenscheme. So that this gives us a construction of free curves which is independent of the behavior of the singularity. So this is the first general construction of free curves where you don't have any hypothesis on the singular points. So I think I'll close with this little example. So we were doing this example of a pair of conics. So when is a pair of conics going to be give us a free thing? And it's going to be free exactly when you contain the eigenscheme. So here's some more behavior of unions of conics. If we have conics which intersect in only 2 points, so obviously you could have 2 conics where you have a triple point and a single point of intersection, then you need 3 members of that corresponding pencil to contain the eigenscheme. And if you take 3 members of the pencil, then that gives you a free arrangement with exponents 2, 3. And if you have the 2 curves meeting in a quadruple point, so there's only 1 point where they meet, but it meets with multiplicity 4, then the union of 2 smooth members of the pencil has the eigenscheme, and that means that 2 smooth members of the pencil give you a free arrangement with exponents 1 and 2. So I should have had a little slide that said, thanks a lot and happy birthday to Frank, but I don't. So that's the end of the talk. What's the takeaway? The takeaway really is that there's this, as I said, there's an interesting problem in combinatorial, I guess I'd say combinatorial / discrete geometry on, if you think of hyperplane arrangements as falling into that class, which is still an open question, which is when is an arrangement free? You can generalize that to hypersurfaces, which if you're sort of a member of the broader algebraic geometry community and interested in Grothendieck's algebraic Durham theorem, then this is essentially saying when does a certain sheaf a vector bundle? So in general, this module of logarithmic forms is not a vector bundle. Sato proved that when you have normal crossings, it's a vector bundle. Here we have non-normal crossings, and yet this freeness condition is that it's not just a vector bundle, it's a vector bundle which splits as a sum of line bundles. So you could ask more generally, for a hypersurface, when is this? When is the sheaf of logarithmic tangent vectors a vector bundle? Or you could ask the finer question, which is what we've been talking about here, which is when is this either a free module if you're a commutative algebraist, or when does the corresponding vector bundle split as a sum of line bundles? And this is even in this very simple case of curves in P2. There's lots of subtle points, and it's something that's also easy to compute billions of examples of. And I'll close with a personal conjecture, which is Turows' conjecture is false. So, and the evidence for this is that there are examples of combinatorially equivalent line arrangements. Neither of them are free, but the degrees of the syzygies changes. So basically what that says is even if you're non-free, you don't have the same degree generators for combinatorial equivalent arrangements. And so there's probably a way, I would think, to push that up and find a counterexample to Turows' conjecture. So good place to stop. I think I was supposed to be 50 minutes and that was 54. So thanks, guys. Let me kill this and stop sharing screen.
Thank you very much, Hal. Are there any questions?
So I have a question about the about sort of genericity in the choice of your curves. I was noticing that in the examples you were able to describe with conics and lines and so on, it didn't seem to matter like what the slope of the lines were when you had several lines passing through the conic, and your theorem was just you would have a pencil and you take any points you want. So are there theorems where you have some collection of curve arrangements, and maybe for a general choice you get something that's free?
This is a great question. So even for lines and conics, what I think would be an interesting question, I actually asked some folks who are in the singularities community about this. So forget about the freeness, right? So let's just talk about behavior of at a singular point of a line and conic. So lines and conics. And so what are the invariants there? Well, we certainly have, and let's even make this an ordinary singularity, right? So I certainly have the list of my slopes, but I also would have the curvatures of the various conics, right? So I have this list of two invariants, the slopes of my tangent lines, the curvatures of the conics. And so is there some condition? And it's certainly true that there is, I think, at least from experiment, I should say, but it's true that there's basically, I mean, you could imagine that there's sort of a Zariski closed set where some interesting behavior occurs there. And that's a very sort of kind of in the circle of the questions you're asking, but even for that example of let me go back to well, I'll just say it. So there was the example of the first example of a non-quasi-homogeneous singularity where we had a nice conic and then four lines that were going through a point of that four or five lines. Four lines going through a point. There are configurations of lines in special position where you actually lose you turn into a quasi-homogeneous singularity. That singularity was not quasi-homogeneous, but for certain special positions, you get quasi-homogeneity. So this quasi-homogeneity, I think, is almost certainly easy. Well, just from the definition of Milnor number and Sharina number being equal, that's basically going to be a Zariski closed condition because quasi-homogeneity says that F is in the ideal generated by the two partials, right? That's what that condition of Riefen or Sato said. And so I think that you generally do see interesting behavior happening, but analyzing that just sort of in the singularities thing, even for lines and conics, the singularity, it doesn't seem to be done. And I think it'd be a fun project to say, okay, here's my list of slopes and curvatures. What's the behavior for something like this?
Al, do you know any irreducible hypersurface in a high dimension of degree 3 or more that's free?
Irreducible hypersurface of degree 3 or more that is free. So obviously, so the first thing to say is obviously if your hypersurface is smooth, it never will be free for the obvious reason that if you're smooth, the Jacobian ideal is going to be empty, right? And so you're never going to have a sort of that freeness is saying that the Jacobian ideal can be written as the Jacobian ideal is if it's a singular hypersurface, the Jacobian ideal or the hypersurface being free says that the Jacobian ideal is given by a Hilbert-Birch matrix. That is the Jacobian can be written as the maximal minors of an n minus 1 by n matrix. I think it should be fairly easy to find irreducible hypersurfaces which are free with some interesting behavior for the singular locus. I don't know one off the top of my head though. So, but I think that would be an easy question to answer. In fact, you know what? I'll send you one by the end. If it exists, I'll send you one by the end of the day.
Thank you. One more.
One other question. From the picture, the early one you showed, but that was basically a braid arrangement in the plane with the
Yes.
coordinate lines and the other.
Yeah.
What about like the braid or the projective braid arrangement in PN? Is that free?
Yeah, those are all free. So those are reflection arrangements. So that so those are free arrangements. Yeah.
Okay, so let's thank Hal once more.
So again, thanks for the invitation. Happy birthday, Frank. And amusingly enough, I'm about to go talk about the cotangent, logarithmic cotangent bundle for a bunch for toric varieties to a bunch of physicists. So, you know, the logarithmic tangent bundle, even though you might think it's an esoteric object, does pop up in lots of places. So thanks again. Happy birthday, Frank. And I got to give another talk somewhere else. So I'm sorry I won't be at the next talk. See you guys.
Bye, Hal.